Okay, so in this video, we will introduce the basic ideas of set theory. Now, all a set is a collection of objects where order and repetition is irrelevant. Let me give you a few simple examples. So we could have the set 1, 2, 4, 5, and 7, and we use curly brackets to denote the idea of a set, a collection of objects. So this set would contain the numbers 1, 2, 4, 5, 7. We could have a set that contains negative numbers, so negative 5, 0, 1, 3, and so forth. We could have the so-called empty set, the set with no elements, and we can denote this also with a 0 and a slash across it. This means the empty set, again the set with no element. Now what do I mean by having order and repetition being irrelevant? Well, let me show you. So if you have the following set, 1, 3, 4, and now what if you change the order and you wrote 1, 4, 3, or 4, 1, 3? Are these sets the same? The answer is yes. They are the same sets as they contain the same elements. Both contain 1, 3, 4. The order is irrelevant, so we consider these sets as being equal. So when we talk about sets, the order is irrelevant, it doesn't matter. And the same goes for repetition. If you ask about the set, say 1, 3, 3, 4, and you ask, is this set equal to the original set, 1, 3, 4? The answer is yes. We do not consider repetition as giving us a different set. This set contains the elements 1, 3, 4. This set contains the elements 1, 3, 4, and they are considered to be equal. You could do the same thing with, say, 1, 1, 1, 3, 3, 4, 4, 4, 4, and ask, is this equal to 1, 3, 4? The answer is yes. This set contains the elements 1, 3, 4. This set contains the elements 1, 3, 4. We disregard repetition, and so they are considered to be equal. And that's it. So always remember, when we consider sets, we only consider the elements within the sets, not the order in which the elements are listed, and not possible repetitions. Of course, if you give me the set 1, 3, 4, and the set 1, 3, 5, those are not equal, as they do not contain the same elements. This set contains the element 5, this one doesn't, and because of this, they're not equal. One other piece of notation is the notation of containment. How do we say in a very concise fashion if an element is a member of the set? So here, 1 is a member of this set, 3 is a member of this set, 4 is a member of this set. Suppose we call this set A. Then we could say 1 is a member of A, but we don't want to write this out, so we use the symbol epsilon. This is a Greek letter E, which stands for containment. So 1 is contained in, is a member of the set A. So 1 belongs to A, as 1 is an element of A. You could also write, of course, 3 is an element of A. You could, of course, write 4 is an element of A. But if you say, what about 5? Well, 5 is not an element of A. To signify the not, you write the epsilon with a slash across it. To say 5 is not an element of A. Okay. Well, one thing that we'll do with our sets is we'll count the elements that they contain. So we want a very simple notation to denote how many elements are in a set, and we use the number notation. So if you write the number sign next to a set, this simply means the number of elements in the set. So for example, if A is 1, 3, 4, the number of elements in A is equal to 3. If your set B, say, was 1, 3, 4, 5, 10. Then B contains 1, 2, 3, 4, 5 elements. The number of elements in B is simply 5. Be careful. If you said C is the set 1, 3, 2, 2, 6, then the number of elements in C is 4 and not 5. 1, 3, 2, 2, 6, but we do not count repetition, so we ignore this 2, and there are only 1, 2, 3, 4 distinct elements, and so the size of C is 4. So always be careful about this, that you remember that we do not count repetition. Okay. Now, what other relationships can sets have with one another? Well, one relationship is the idea of a subset. And very simply, a set is a subset of another set if it is contained in that given set, if every element of the first set is an element of the second set. Let's consider a simple example of this. Take the set A to be 1, 2, 5, and the set B to be 1, 2, 3, 4, 5, and 6. Let's take one other set, C, to be the set 1, 2, 4, and 7. Well, if you notice, every element of A, 1, 2, 5, is an element of B, 1, 2, 5. And so we say A is a subset of B, as every element of A is an element of B. And we write quite simply A, and we use this symbol, a C with a bar underneath it. This means a subset of, and so A is a subset of B, as every element of A is an element of B. What about C and B? Is C a subset of B? Well, 1 is in B, 2 is in B, 4 is in B, but 7 is not. And so as 7 is an element of C, but not an element of B, C is not a subset of B. And that's it. That's the notion of a subset. Now, one question is, can we do algebra on sets? Can we operate on multiple sets at the same time? The answer is yes. And there are basic notions. There's a notion of subtraction, then of union, intersection, and then the notion of complement. So let's start quite simply with the notion of subtraction. Let's look at B and A, for example. Could we make sense of B minus A? The answer is yes. Think of it as you start with the set B and you subtract A, so you throw away every element in B that is found in A. So you start with the set B, 1, 2, 3, 4, 5, 6, but you subtract the elements that are found in A. So as 1 is in A, we remove it. As 2 is in A, we remove it. As 5 is in A, we remove it. And so B minus A is the set 3, 4, and 6. And that's it. So think of subtracting sets by starting with the initial set and removing the elements in the other set. That's the notion of subtraction. Now we have two other basic operations, union and intersections. Let's consider for this A and C. So we write A union, so a small UB, and this means take all of A and all of B and dump them in a larger set. So an element of the union between A and B is a member of A or a member of B. So we take all the elements in A, 1 through 5, and we throw in also all the elements, whoops, I meant A union C, sorry, A union C, and we throw in all the elements of C 1, 2, 4, 7. Of course, we can simplify now, as we do not consider repetition and order, so we already have 1, we already have 2, and so we're left with A union C being 1, 2, I'll put the 4 first, not that it matters, 5 and 7. That is A union C. Put all the elements of A and C together. Of course, disregarding repetition and order. So, an element is in A union C if it is either an element of A or an element of C. The other notion is intersection. So we write A, and then we flip the U for the assertive cap, C, A intersects C, and now the word gives it away here. Intersect means what is common, where the two sets overlap. So what is common to A and C? Well, 1 is a member of both A and C, so it is in the intersection. 2 is a member of both A and C, it is in the intersection. 5 is in A but not in C, not in the intersection. 4 is in C but not in A, not in the intersection. And 7 is in C but not in A, not in the intersection. So A intersects C is quite simply 1, 2. And that's it. The union dump the two sets together into a larger set. The intersection only keep the elements common to both sets A and C. So there you go. Subtracting sets, taking their union and their intersection. Now there is one other key idea, and that is the idea of the complement, but that is relative to what's called a universal set. For us, and we'll see this through examples, a universal set will be the set that contains all of the possible outcomes of interest. We'll have an experiment, we'll look at possible outcomes, and the ones that are of interest to us will form our sample space. So suppose we have A is a subset of S. S again is a big set that contains all of the elements of interest. Then we can form the complement of A relative to S. So we write A with a little c in the exponent. This reads A complement. And here's how it's written. So we write X. So what are the elements? Well, they are elements of S. So we write X as an element of S. And it must satisfy one more condition. It must not belong to A. And that's it. So again, this notation means the first part is what are the elements of our set. They are elements of the larger set S. The second part after the colons is the condition or conditions that our elements must satisfy. So here we're saying the elements of A complement are the elements coming from our larger set S that are elements not in the original set A. So think of the complement quite simply being everything that is in S but not in A. And that's it. Of course, if you write S complement, then you're asking for everything in S but not in S. As S contains everything of interest, we get the empty set. And that's basically it as far as operations on sets. One key idea, especially when we consider problems of counting and probabilities, will be how can we visualize all of these operations and these relationships between sets. And the idea is quite simple but remarkably useful, and the idea is that of a Venn diagram. So let's consider an example for each of our basic operations: union, intersections, complements, and subtractions. So the idea of a Venn diagram. And this will be really useful because as you'll see, the idea is very intuitive and it gives us a way of representing sets and their relationships with one another geometrically. So we'll think of sets quite simply as regions in our larger set S, which we'll call our universal set. Suppose we started with a union B. Well, in every example, we'll have a set of all possibilities. This will be our set S. And we'll always consider S as a rectangular region. So in this rectangle are all possibilities for our experiment. We can view set S, not S, but A as a region, and set B as another region. And when we think of A union B, we combine all of A and all of B together in this larger region. And that is A union B. What about the intersection? Well, if we intersect A and B, let's reproduce, and this is the so-called Venn diagram, our so-called universal set or sample space S. Region A set A, region B set B. Now the intersection is obviously quite different, right? We don't dump all in A and all in B together. We only take the elements that are common to both A and B. That is the overlap between A and B. So it is this region right here. And this is A intersect B, the region common to both A and B. What about the subtraction? A minus B or B minus A. Doesn't matter. Once again, we draw our Venn diagram, our sample space or universal set as a large rectangle. A and B may overlap each other. And A minus B is the set that contains all the elements that are in A, but not in B. So we take all of A and we throw away what's in B. That is the overlap between A and B. And this gives us, of course, this region. This is the set A minus B. Everything in A, but not in B. What about the idea of the complement? If we have a set A, how can we view its complement in the Venn diagram? Well, we have our universal set S. A is a set or region in our Venn diagram. So this is A. And if you remember, a complement was every element in S that is not in A. So everything except in A. So of course, that is exactly that. Everything in our universal set except the elements that are in A. So this is now a complement. Everything but A. Let's look now at one principle of counting because again, the idea of sets will be useful as a tool of counting, especially the notation and also in terms of probabilities. Let's look at one simple counting fact that is the so-called inclusion-exclusion principle, which is extremely useful and also in terms of probabilities, but very simply figured out with the help of Venn diagrams. So let's look at this. The inclusion-exclusion principle. And the question is, what if we want to count the number of elements in A union B And we know the number of elements in A, in B, and in the intersection. Can we somehow figure it out? Well, we'll start with a Venn diagram. So suppose we have our sample space S, the set that contains all possible outcomes in our experiment. We have region A, set A, region B, set B. And the idea of this principle is when you have a large set to count, it may be difficult, so you may want to break it down into smaller sets, and usually smaller sets are easier to count as they contain fewer elements. So, we asked, what is the size of A union B? So how many elements are in A union B? Well, as we know, A union B is all of A and B put together. So the number of elements in this bigger region. Well, let's start counting. Let's add all the elements in A first. And I'll shade A now with vertical bars. So we've counted every element in A once. Okay, well we're missing now the elements in B. So let's add plus all the elements in B. Let me count them using horizontal bars. And now you may of course ask, is this the right number? If you look at the picture, you can clearly see that the answer is no. When you count the size of A union B, you have to count every element in here once. Well, we've counted what's in A but not in B once. We've counted what's in B but not in A once. But if you notice, we've counted the elements in the intersection twice. Once when we counted the elements of A, the vertical bars, and twice when we counted the elements in B. We have to count the elements in the intersection once. Well, if we counted those twice, if we remove them once, we'll be left with counting them once. So we have to remove the size of the intersection. And that is the so-called principle of inclusion-exclusion. So the size of A union B is the size of A plus the size of B minus the size of their intersection. And that's it. And you can see how this may not look so obvious at first sight, but once you look at it with the help of a Venn diagram, it's actually fairly straightforward. Let's look at one last set operation, and that is the Cartesian product. This will be useful when we consider sequences of events or sequences of selections. Once again, this will be used in counting sequences of selections. So this is, as I've said, the Cartesian product. Let's start with just two sets. You can do A, and we use a little x times B. And this is the Cartesian product of A and B, so A times B. What it is the set of tuples. So here we have first element A, second element B, where obviously the first element must be a member of A, the second element must be a member of B. And that is the Cartesian product between A and B. That will be a sequence of two selections. Choose something from one set and then choose something else from a different set and keep track of the order of the selection. You could of course repeat this over two sets. You could do A times B times C. Now instead of a tuple, you would have a triple. So result of the first selection, then the result of the second selection, and the result of the third selection, where obviously little a is a member of set A, little b is a member of set B, and little c is a member of set C. And this obviously generalizes over 4 sets, 5 sets, and so forth. And now we'll ask quite simply, what is the size of A times B if we know the size of A and the size of B? Let's take a very simple example, and then we'll figure out that this actually always works. So what if A was simply 1, 2, a set with 2 elements, and B was a set with 3 elements, say 4, 6, 9. Let's look at all the elements of A cross B. Well, they are tuples where the first element must come from A, the second element must come from B. So let's fix 1 first. Then we can have 1, 4. We can have then 1, 6. And we can have, of course, 1, 9. That's 3 elements. By fixing the first element of A, well, we could have fixed 2, the second element of A. So then we could have 2, 4. We could have 2, 6. And we could have, finally, 2, 9. And that is A times B, the Cartesian product of A and B. Now, let's see. A had 2 elements. So the size of A is 2. B had 3 elements. The size of B is 3. Let's look at now counting the size of A cross B, or A times B. 1, 2, 3, 4, 5, 6 elements. And if you notice, 6 is 2 times 3. Whoops. 6 is not the set, but the size of the product of A and B. So 6 is equal to 2 times 3, but 2 is the size of A. 3 is the size of B. And you can see that with this example, the number of elements in A times B is quite simply the number of elements in A times the number of elements in B. And this is always true. So if you take the product of 2 sets and you ask how many elements do I have now in this new set, the answer is the number of elements of the first times the number of elements of the second. Of course, if you had A times B times C, and you ask, well, what's the size of this? It would be the number of elements in A times the number of elements in B times the number of elements in C. And this, of course, does generalize to any number of Cartesian products. You could have A times B times C times D, same thing, and so forth. And this will be a very useful principle of counting when we consider again sequences of selections, where we keep track of what was selected first, second, third, and so forth. And that's it for set theory. So remember that if you ever have difficulty figuring out what happens with sets, you can always use Venn diagrams. We'll use them over and over again in counting and probabilities. And when you have a sequence of selections, you can view this as a Cartesian product. And if you know the size, of each set, it's easy to find the size of the Cartesian product. And that's it.